The next topic is light as a dual-natured thing. Thing's probably the best way to put it, because I can't say particle because sometimes it isn't, and can't say electromagnetic spectrum because sometimes it isn't. So we'll talk about the dual nature of light. All right, so light's dual nature can be shown in two ways. So first, we're going to talk about light that acts like a wave. All right, so we've already shown wavelengths and frequencies, so that seems like there should be waves, right? Light should be acting like a wave. The two independent observations we're going to talk about are refraction and interference. So light will undergo refraction and light will undergo interference. So light given whatever wavelength we're talking about, its speed. I mean, you could say it's the speed of light, but a speed of light is that speed that we've not calculated, but actually determined in a vacuum. And then if it goes through any object, it actually slows down. So if it passes through glass, it slows down. If it's passing through the atmosphere, it slows down. Not a lot, but the speed does actually change depending on what it's passing through. Okay, when light hits an object of a different density than the object that it's passing through, so if it's passing through the air and then hits water or hits glass or hits plastic, then the light actually changed directions. That's called refraction. So when you know this phenomenon with rainbows. So the light is passing through the air, it hits the water in the rain, and then the light bends. Depending on what wavelength we're talking about, the light will bend more or less. So that's why we get a spread pattern of white light where we get the whole rainbow, because the purple light bends at a different angle than the red light or any of the lights colors in between. Bends probably not the best word, just turns, angles. It doesn't, when it goes through, it doesn't arc, it actually makes angles. So depending on what wavelength we're talking about, we would get a different angle, and it's instantaneous, going this direction, and then now I'm going a different direction. So I'm going through here and I pass through a different median, and then I turn. There is no curvature to the turn, it is an angle. Okay, so we see this, like this pencil right here. That's not very big. Can I make that bigger? No, can't make that bigger. I can make the whole thing bigger. So this pencil is obviously not broken. It's just a pencil that's going through air and then going into water. And so the fact that the light hits the pencil and then when it comes out of the water, it turns, that's what gives you the perception that the pencil is broken, because the light is actually not in the spot where the pencil is. Because as it leaves the water, it turns itself. This is why when you're standing in a swimming pool and you look down, your feet are not right below you. This is what makes spearfishing difficult. You think you know where the fish is, and then you go to stab the spear in, and then the spear misses it because it's going to be offset, because you're not looking at the spot where the fish is, you're looking at the reflected light as it's bent coming out of the water. So the way to spearfish and make everything work well for you, just in case you're Tom Hanks and you're in Castaway and you make yourself a spear, put your spear tip in the water, because then the fish that you're trying to stab and the spear are both offset by the same distance. So if the fish is 1 inch to the left of where you think you are, the spearhead is 1 inch to the left of where you think it is. And so then you angle the spearfish into the spear into the fish, and it'll work better for you instead of having it out of the water and stabbing it into the water. When I see that, I'm like, that's not likely. You can also see this effect if you take an ice cube, like get some water, some room temperature water, and then put an ice cube into it and look at it very carefully. You will see swirls around the ice cube. And what's happening there is the water itself right next to the ice cube is colder than the rest of the water. So the light is going through and hitting that different density water and bending it. And that bend in your head is shown as a swirl. And then a really easy way is this mirage. So there's not water on this ground. We know this. This is just a mirage. And so what's happening is this asphalt heats up, and then the air right above the asphalt gets super hot, and its density goes down and it rises up into the atmosphere. And then colder air replaces it. And so you get this constant effect of air being replaced, air's density decreases and it rises, and higher density air replaces it and it gets heated, its density drops and it rises. So what you have is the light right here that's trying to get to you from this road is having to zigzag through to get to you. And the light right next to it is zigzagging. And since the nature of the air rising is so chaotic that they don't come to you parallel, which is where they left the source, they get all jumbled. So what you're seeing is a jumbledness of the light that's supposed to be just a reflection of the road. I mean, it's supposed to look like asphalt, but here it doesn't because of this jumbling. As the light has to pass through different densities, it turns and turns again and turns again. By the time it gets to you, it's turned like a million times, and so it's not at the they don't all line up when they get to you. This is also what keeps light inside of fiber optic cable. So if you've seen lamps, fiber optic lamps, maybe I could just pull a fiber optic lamp up. Fiber optic lamp. These were kind of cool when I was a kid, and they're not really a big deal anymore. But here you go. So the light is passing through this cable, and then it comes out the tip. So these ones are. This is not what the fiber optic cable looks like from, like, if you have fiber at your house or what the internet uses. This is specifically some light that is allowed to escape through the sides of the wall. If this was fiber optic cable, you would just see light at the tips. True fiber optic cable would just have light at the tips. So you shine the light in one end, and it hits the inside of the fiber wall, and then bounces back in, and then hits the wall on the other side and bounces back in, and then it just ping pongs itself all the way to the end. And that's how fiber optic cables work. Okay. All right, so we should be able to agree that light is acting like a wave because it's refracting. This is what waves do, they refract. Okay, the second observation is something called interference. So interference sounds like stuff getting in the way, but actually what ends up happening is the two different sources of light or two different wavelengths of light will interfere with each other in a way that's constructive or destructive. And the constructive interference means that it makes the light brighter, and destructive interference means that the light is more narrow. Not narrow, but it makes it more dim. Okay, so here's the experiment that gets done. You have a flashlight, and over the flashlight, you put like a piece of duct tape, and then you slice with a sharp knife, a small slit in that duct tape, and then you shine it at a wall. Okay, so you would just get a stream of light that's coming out. So the analogy to that, or the analog to that would be, let's say we've got water and ocean. And so when I was in the Navy, there were bridges and tunnels and wave breakpoints in the Chesapeake Bay. So the ships didn't have to experience really heavy duty waves to smash them up against the pier. So what they did is they built these brick wall things. And so there was like an opening in the brick wall and an out, entrance and exit kind of situation. But when these big waves hit this wall, what would happen is you would have one wave, the wave here makes its way through just a little piece. And then instead of just being straight, instead of just being like a little piece of wave that continues, it arcs its way out. In the same way that when you throw a pebble into water, you get a ripple effect in all directions. So this way, the ripple is only 180 because the backside is blocked. And so you get these different sections where the wave is arced out instead of it being coming in straight. And it's also obviously much smaller because there's only a portion of the wave that's making it through. Alrighty. Well, what happens if you put two of these things adjacent to each other? So I have this hole where waves come through and this hole where waves come through. You can imagine that the waves are coming through and the waves are coming through on this other side. And sometimes they run into each other where they're both the crests are right there, so they're both tall, which makes the wave taller. And then sometimes they run into each other where the crest is up and the trough is down, and they run into each other and it makes it flat. So these sections of destructive interference, there'd basically be no wave motion there. You would barely bob in the water at all. But right next to it, this section of constructive interference, you would be bouncing up a lot. And it would be very close to the section where there was destructive interference. It seems counterintuitive, but this is absolutely the case. If you are a boater or have spent any time with fishermen, they will tell you when they're entering and exiting these constructed wave barriers that this is absolutely something that happens. It also happens naturally because under the water there will be areas of elevated land and valleys. And so those valleys and little mountains off the coast cause the water to come in at different arcs, and then you get this constructive and destructive interference. When you're walking along the beach, it's rarely a walk that's like this. It's usually a walk that's like this. So this would be constructive if this is land and this is ocean. This is constructive interference, and this is destructive interference because the soil or the sand here is sticking out, which means it's not eroding away. It's not getting hit hard. Where this sand over here is getting hit hard because the waves are building up on top of each other. You can look at the coast, the Oregon coast, and this is what it looks like. As you go down the coast, you have this. So if you're in a house that's built right here, maybe that's not a great place to have your house because obviously nature has been using constructive interference to have waves that are bigger than normal, and then they're eroding away that land. If you have a house here, you're probably much safer because this is an area of destructive interference. And that means the waves kind of cancel themselves out. So they're not hitting those cliffs as hard, so then they don't erode. Okay, so we know that water waves will do constructive and destructive interference. All right, so what about light? So let's go back to our flashlight. This time we have our flashlight, and then we put our piece of duct tape over and we put 2 slits in it, like X-Acto knife slits. So what you would expect is you get light here and you would get light here, and that's it. But what you do get is light in those spots where you expected, and then you get a dark band, and then you get a light band, and you get a dark band and a light band. What's happening here? You have, this is destructive interference, and this is constructive interference. So this is where the light builds up. So you get these bands. You can do this at your house. Seriously, just take a flashlight, put a piece of duct tape over it, make 2 slits in the duct tape that are parallel, turn the flashlight on and point it at a wall. You will get this pattern. This spot right here and right here will be the brightest, but you will also get a spread pattern of the constructive and destructive interference. So we can say light is a wave because it undergoes interference and it undergoes refraction. So without a doubt, light is a wave. We're going to move on to something else in a sec, but I do want to talk about something else up here. Let's give you one more example of this refraction stuff. So here's a terrible picture of a truck. All right, so light, sunlight, passes through the windshield, and when it passes through the windshield, it turns. And let's say I'll put a seat right here. And that light impacts this seat, and that seat absorbs that energy, and then that seat becomes warm. We've all experienced a too hot seat in the summer, or a nice warm seat when it's a cool day outside, but there's full sunlight. So that seat gets warm, and then that seat radiates light you cannot see in the form of infrared light. So light that has wavelengths longer than red light, and that is re-radiated, and it hits this windshield, and the crazy thing is it bounces back in and heats up the floor or the steering wheel or the dashboard. It can't escape. So the reason that you have a car that's warm, let's say it's 40 degrees outside, but the car itself is in direct sunlight. There's no clouds that day. The inside of your car will be warm. You haven't done any heating of it, but the sun has, because this is the greenhouse effect. The light is reflected back in. Once it comes in, it's not much of it is allowed to escape. Some of it escapes because you can see what's inside the car through the windows, but a lot of the radiation that entered the car is now stuck in the car as infrared radiation. So do not put your animals in a car, even if it's 40 degrees outside with the windows rolled up. It will. I did this experiment. It was 45 degrees one day. I put a thermometer in the car. I closed the door. 7 minutes later, I came back and it was 115 degrees in the car. It was 45 degrees outside. So again, it is legal in the state of Oregon to break a window or force a door open to let an animal out, as long as immediately following that you contact the police. Okay, so we said because of this refraction and because of this interference, that light is definitely a wave. And so now I have to tell you that light is not a wave. Light is a particle. So what do I mean by that? All right, so this is something called the photoelectric effect. This is actually what Albert Einstein won his Nobel Prize for in 1905. He published this in 1905 and won the 1921 Nobel Prize. So he didn't win it for a theory of relativity, E equals mc squared, any of that kind of stuff. It was for this idea. So him and Max Planck, that's the Planck's constant guy, they couldn't figure out what the situation was. The calculations that they were doing using traditional physics didn't work. But Planck had a crazy idea, and Einstein concurred that what if instead of thinking about light as a continuous spectrum, that light isn't continuous, that is truncated. It comes in small packets. The packets that they use, the name that they gave these packets were quanta, and this is where quantum mechanics comes from. So I'm gonna make a drawing here. Bad drawing, of course, because it's me. All right, so okay, so let's say this is a little piece of music. Okay, high notes, low notes, spaces in between, whatnot. And you wanted to make a digital recording of this. So somebody's on the stage singing with a guitar, and this is what your recording device would come up with. If you recorded with your phone, what would end up happening is you would get sections, pieces of the music. You don't get the whole thing. But in the same way that movies are literally still pictures that are ran quickly, just like a flip book, your body, your eyes, your brain can't tell the difference between that motion and the fact that really what you're looking at is a bunch of still photographs. So inside your phone, you're storing this digitally, and you're storing a piece of the music. And then the gap from here to here, your brain fills in all by itself. So you don't really need it. So you would, if the recording was bad, you would notice that. So let's say instead of the sections of the music that you're recording, you recorded at a lower setting. So you can record at different settings, like there's a 128, there's a 256, there's a 512, there's a 1024. There's definitely less than this. I think there's a 44 and maybe a 64. Anyway, this is samples per second, meaning it took 44 pieces of information per second. And this is what people use for podcasts or for audiobooks. Because it doesn't have to sound good. You just have to be able to understand what they're saying. And this would be an actual CD. If you still have an actual CD, one from like an actual company that created a CD, not like a person making it with their MP3s. And so you can see that there's a lot more information. So I can have it, let's say that this 1024 are these blue dots. And then the 44, that would be more like this. No, not that much. So it's a lot less information. But if it's just speaking, then you most likely can understand what the person's saying. But if we're talking about multiple instruments playing at the same time, you're not getting the full effect of what the person is trying to instill on you with their music. So what Planck and Einstein said was, light acts like this. It acts like it comes in little packets. Instead of a continuous wave, you get this photon of energy. Okay, photon of energy. How? Well, but we already know that it acts continuously because we already know that it undergoes a type of interference, and we know it undergoes a type of refraction. So how could this be like a packet? Okay, so here's the example. This is basically the way a solar panel works. Here, oops, whoa, there we go. So you've got a metal or a metal alloy or a metal mixed with some other stuff. And if a certain frequency of light runs into it, wavelength of light runs into it, an electron can be released. Okay, the electron is released. And this electron can, I don't know, it doesn't really matter. It could power a light or power a solar power calculator. You can do anything you want with it. It's just electricity. So what they decided, they did this, and so the green light that they shined on this produced an electron. Awesome. Okay. Well, oops, sorry, I didn't mean to do that. Not to do that. They tried something else. They shined red light on it. And nothing happened. The electron did not get bounced out. Okay, well, that makes sense because red light has less energy than green light. So, okay, it hasn't reached the threshold to knock the electron off of this metal. Fine. So what would happen if they used two red lights at the same time? So the energy of these two is greater than the energy of one green light. So it should work, right? The answer is no, it didn't work at all. The reasoning is that the electrons can't, or the light, the wavelengths of light can't hit the electron at exactly the same time. So if one red light hits the electron and then the next red light hits the electron got a burst and then it went back down to its normal state and then got another burst and went down to its normal state. So together, they never acted together on it. My example for this is, if you've ever moved a refrigerator, it usually takes two fairly strong people to move it. Okay, what if you had 35-year-olds? How much weight could 35-year-olds lift? Well, I know my 5-year-old can lift at least 30 pounds. Okay, so 30 pounds times 30 5-year-olds. That's 900 pounds. Can two guys lift 900 pounds? Certainly not two normal guys, like maybe two guys going for world's strongest man kind of situation. But you can't do that with two people. So the 35-year-olds are actually stronger than the two men, the two big people who are lifting this fridge. But it doesn't matter that the 35-year-olds are stronger, have the ability to lift more, because they can't all act at the same time. This red light can't act at the same time as the other red light, so they can't impart their energy on that electron at the same time, making the electron eject and go through the circuitry. But the green light can. So solar panel, there we go. Solar calculator, same situation. This is powering this person's house. This is powering that calculator. So if you were to shine red light at that calculator, the calculator wouldn't turn on. But if you shine blue light at it, it would turn on. So these two light sources, if you haven't seen this one on the left, this is usually at a buffet or maybe like a function, like a wedding or a birthday party or something, and they're trying to keep this prime rib, or in this case, I don't know what that is, probably ham. They're trying to keep it at a temperature above 145 degrees so bacteria can't grow on it. So it can be available to everybody during the course of the meal. This light is big. This is one of these lights that's like a normal light bulb would be like 40, 60, 80 watts, something like that, of the traditional light bulbs that are incandescent, not the LED ones or the compact ones. And this thing would be like 1200 watts. This is like something that if you plug it into a bad outlet, it pops a circuit breaker kind of thing. That light is huge. If you put your hand underneath there, your hand will turn to 145 degrees. It will be uncomfortable. So there is a lot of energy coming out of there. On the right here, I've got a pen light that's running off a quadruple A battery. That's it. One quadruple A battery. The pen light will turn on that calculator. This calculator will be turned on by that blue light. But this red light cannot turn the calculator on, because even though there's tons of energy here, they're acting independently of each other, and each one individually cannot raise the energy of that electron to eject it. Where the blue light, even though it's not very much energy because there's only a few of these blue lights coming out, I would not be warmed by this blue light. Each one of them has enough energy to eject it. Another analogy would be, let's say that you stood in front of a staircase and you lifted your foot up halfway and tried to step up to the step. You would not make it. Well, what if you lifted your foot up 50 times and each time you lifted it halfway? Would you ever make it to the step? And the answer is no, even though you put in much more effort than if you would have just lifted your foot up all the way to the height of the step one time. You put in tons more because you lifted it up 50 times halfway. It still doesn't get the job done. It still doesn't get you to the next step. So there is a threshold that must be reached, and you can't add these things together to reach that threshold. So now we think of light as a particle instead of a wave. Except we already know that light refracts and undergoes interference. So this is the dual nature of light. Depending on the circumstances, it acts like a wave. And if the circumstances change, then it can act like a particle. Yeah, we don't know enough about it yet, but that's where we are now. There is a dual nature to the light. So there's an atomic version of this. The atomic version of it is atomic line spectra. So what is atomic line spectra? This is sort of a fingerprint for an atom. So if you've got a sample, we'll make it easy on ourselves. Let's say we have a sample of hydrogen gas. We have it trapped inside of a glass container. And that glass container, sort of like an old fluorescent light bulb, looks like that, and you run electricity through it, what you'll get is the electricity goes through and is hitting the electrons on the hydrogen atoms, and different things happen. So if these are the different energy levels, energy level 1, 2, 3, 4, 5, 6, and 7, and we know there are 7 energy levels because there are 7 rows on the periodic table. So the electron for hydrogen is 1s1. That's its electron configuration. It's only got 1 electron, and so it's in energy level 1. So it's here. So I got this 1 electron, and if it gets energy from the electricity that's being passed through the light, that electron could jump to another energy level. When it jumps to another energy level, it has absorbed the energy of whatever the electricity passed through it. It will not stay there, not even for a nanosecond. It'll drop back down. So this, when it's up here, it's called, it's being in its excited state. And then this thing is going to go right back to where it came from. It's going to drop back down to where it first had. When it does drop back down, it has to give back the energy that it absorbed to get up there. So some form of radiation comes off of it. Could be green light, could be blue light, doesn't really matter. A light could be infrared. You might not be able to see it. Could be X-rays. This is how we generate microwaves, depending on what the situation is. So I can make the electrons jump. So you can think about the energy levels as sort of like stairs. Where can the electron not jump? It can't jump to right there. That's not possible. It has to jump to a spot. This would be like you being at the bottom of the stairs and trying to jump up and land at stair 3.5. There isn't a stair 3.5. You can land on stair 4, or you can land on stair 3, but you can't land on stair 3.5. There is no spot for this electron to be. So it would not absorb whatever this energy it is to go from there to there, would never be absorbed by that electron because it can't absorb energy and put itself nowhere. Okay. So what do we have all these colors for? We have all of these colors because if this electron here jumps up to here, it could jump down to the other thing that can happen is instead of it jumping right back down to, say it jumps all the way up to number 7, it might not jump all the way back down to 1. It might jump down to 5, and then to 3, and then to 2, and then to 1. And each time it's going to release some sort of radiation. Every atom will do this in some fashion, either skip all the way down, jump all the way from the top of the stairs all the way to the bottom, or jump down a few stairs and then jump down a few more and then go back down to its ground state, as close to the atom as it can possibly be. Depending on what jump it makes, so in this case, what we're showing is if the atom were to jump from energy level 7 and jump all the way down to energy level 2, it would give off blue light. But if it jumped from 6 down to 2, it would give off green. That makes sense because blue has more energy than green. And then yellow has less energy than green. And we can see that because the drop from spot number 5 down to spot number 2, it doesn't need to release as much energy to do that. These other ones, this is like our infrared series. So this is saying if it jumps from 7 down to 3, it didn't jump that far. So the light that it gives off is not visible light. It's actually heat light in the form of infrared. But if it was to jump from 7 all the way down to 1, it would give ultraviolet light, light again that we could not see, but has more energy than visible light. And then in that case, we would be not want to be around that light because it could cause cancer. Okay, so this is another reason why we can say that light has a dual nature and is a particle, because the electron here will absorb only a specific packet of energy. I cannot shoot multiple energies at it, have them absorb at the same time and jump up anywhere. That's not possible. It has to be one photon of light. When we do this, well, let's show you, let's say this is, what element is this? So this would be 1, 2, 3, 4, 5, so 3p4. 3p4, so I grab my trusty periodic table, go to row number 3, and go over to the P block and go to column number 4. 1, 2, 3, 4. So this is sulfur. Okay, so I've got my sulfur atom. So this is my sulfur atom. And I know that because it's in ground state. This is an excited atom. So you would do atom and you'd put a asterisk there. What's happened here is that electron right there has received some energy and it shot itself up to the 3D. That's what we have here. What's going to happen is that electron is going to fall back down to the 3p. And when it does, it's going to give off some light. So if you hit sulfur with a certain type of electricity, it will glow a particular color. Each atom has a very specific color. So if I pass the light that's being generated by that substance that is releasing energy after it gets hit with energy, you'll get a spectrum. This is hydrogen. This is what it looks like for hydrogen. So instead of having the full rainbow, this is basically sunlight. This is just hydrogen light. So I get 1, 2, 3, 4 wavelengths. Why only 4? There's only one electron, and there's only so many places that electron can fall to, and these are the colors that it's going to produce. The combination of these colors is sort of a, I don't know, pinkish hue. In the same way that if it was blue color and red color, you'd end up seeing a purple color. So these color combinations together give us this pinkish color. It's dependent upon the colors that are produced and the intensity of those colors. If the red is super bright, which it is in this case, it overshadows the 2 purples down here in this light blue or teal, whatever color it is. And so it wants to come through as red, but these colors are changing it a little bit to make it more of a pinkish hue. But if they were all the same intensity, I don't know what color we would get. Something closer to the blue spectrum because it's we're more on the energy end there. Okay. This is what neon looks like. So if you've seen neon lamps, so not all lamps are neon lamps. Those are gas lamps, but if it has neon in it, you specifically get this super bright orange color. And if you were to take a prism and let this light go through the prism, this is the crazy thing that you would see. Some greens, some yellows, some reds, a little bit of orange. And together, all of these colors add up to that color. This is electrons jumping up and falling back down. Every single one of these lines is an electron that has gone up to some excited place and then fallen back down and released one of these colors. And since there's lots of electrons and lots of atoms in there, it happens a lot. And so we get this color out of it. Already talked about that. I'm going to talk about this calculation for, it's in your book. People are going to talk about it if you take a higher level chem class or a physics class. This is calculating the amount of energy that you would get from a fall from one energy level to another. So these ends are my energy level. The energy level that I landed on, the energy level that I started off, I square those things. I use this number up here, which is a combination of two other constants. And then I can subtract my energy final minus my energy initial to get the energy of the fall. And the reason I don't really care about this equation is the equation only works for hydrogen. That's it. No other atoms. The moment I've added a second electron, this equation fails. So it's cool. It's fun. It's nice that somebody calculated this, but it doesn't work after the fact. The second I've added a second electron, so it does not work for helium or any other atom. But you could calculate the amount of energy that a hydrogen atom was releasing. Let's say that it went from energy level, it was at energy level 2, and then it went up to energy level 5. How much energy would it take to do that? And then you would also, you could say, well, if I went from 5 down to 2, how much energy would I get out of it? Works both directions. This next emission spectrum, so the fingerprinting, this thing here, this is called an emission spectrum because I'm giving stuff energy and then it emits light. This is the emission spectrum for sodium. It's kind of unusual because it's sodium. I'm going to put it in yellow because that makes sense. It gives 2 lines and that's it, just 2 lines. And those 2 lines are really, really bright, so bright that they overpower other stuff. So when you're looking at fire, if there is any sodium present, and sodium is in most living things, so it's definitely in wood, you're going to see yellow. So that's why the flame itself is mostly yellow. And if you burn like a propane, there's no yellow there. There's no yellow because there's no sodium. But if you were to take some table salt on your barbecue grill and sprinkle some table salt into the flame, you would see yellow. It would overpower that blue color. It is that bright. The street lights in low value areas, I say low value, you're not going to see street lights that are sodium lamps like in downtown Portland because people want to see things nicely. They want things to look good. And this light is kind of gross. You can see with it, the light in front of the college and the Dalles is a sodium lamp. It's yellow. It like makes everything not look good, makes everything look a little sickly, but you can see it. So if a cat runs out into the car at 3 o'clock in the morning and you're driving there, the cat doesn't look great. I wouldn't want to take a picture of that cat with that light, but that cat is visible to us. And the reason that they would use the sodium lamp is money. It's incredibly cheap to run that sodium lamp night after night after night because it produces these 2 wavelengths in the visible spectrum at a low energy cost. So I remember being like 7 and they decided to put street lamps in my neighborhood and the cost was going to be like 3 or 4 cents per month for 20 years to pay the whole thing off for the whole neighborhood. Everybody has an extra 3 or 4 cents on their electric bill every single month for 20 years, and then the lamps would be paid off. Actually, I think it was more like 6 cents, and then after 20 years, it dropped to 3 cents. I think that's what it was. So you paid for the construction of them, and then you continually paid for the cost of the light itself. Okay, so what's this next thing? This next thing is called an absorption spectrum. So the difference between an emission spectrum and an absorption spectrum is interesting. So in the absorption spectrum, what you have is, I have this container, and inside I have sodium as a gas. We can totally turn sodium metal into a gas. And over here, I have a light, and this light is shining out white light. Sorry, it's purple, but it goes through. So there's white light that comes through, it passes through here, and all of it gets through, except these two yellows. So you'd end up with a spectrum that looks like a full rainbow minus these two lines of yellow, because the sodium's electrons are absorbing that energy, and then they're releasing it, but they're not releasing it this direction, they're releasing it in every single possible direction. So 360 degrees of a sphere, so you're not going to see it. A little bit will leak through to your detector, but most of it just goes off in any old direction. So why is this important? Well, we can set up a facility that instead of you having to run electricity through the substance, we can just gasify the substance, put it into a container, and then run regular white light through. It makes it a little easier. But the coolest part about it, let's do the coolest part. So let's say really far away from us, there's a sun. And there is a planet that rotates around that sun, okay? If that planet has an atmosphere around it, the light from this sun will pass through that atmosphere. And if way over here is Earth, we are receiving light from that sun. But the light that passes through that atmosphere, these wavelengths of light, are missing waves in the same way that this rainbow is missing. And so that's how we determine what the atmosphere consists of. So if the atmosphere corresponds to sulfur dioxide, we probably don't want to go to that planet. If the atmosphere corresponds to fluorine, we don't want to go to that planet. But if it's oxygen mixed with nitrogen, we would want to go for that planet. So that's why every once in a while you hear in the news that we found another viable planet. I think we're up to close to a dozen viable planets as far as the atmosphere goes. We don't know anything about it. So other than the fact that it's the correct distance from their sun, so it's in what's called the Goldilocks zone, and it's the correct size, meaning it's not too small, it's not too big. It wouldn't crush us with its gravity, and it wouldn't make it so light that it would be difficult for us to move around on. And it's got what we perceive as a breathable atmosphere. So that's pretty cool that we can determine the livability of a planet that's many light years away from us. So we just have to make sure that that sun lines that planet is right in the middle in between us and whatever that sun is. What else? Anything? I'm just talking about that. Nope, that's it. That's all I'm going to do for this lecture. Thanks.